So the plan today is to just continue on with induction. So last time we were just kind of building some intuition about why this process might be useful, playing that game of NIM. So today we'll be working with worksheet 13. So you might want to have that open, dealing with proof by induction. So this is chapter 2 material. So before we get started, are there any questions? Okay, so then just to kind of recap what you read about or watched for the reading quiz. So proof by induction is like this domino knocking over. I think that analogy is very powerful and appropriate here. So we want to prove a statement which is dependent on some integer n. And so the way that we can do this is we consider the first case for n, considering the base case. So what's the smallest possible value that n can be? We try and show that that's true. So in other words, the first domino falls over. And then the induction step is the step which is saying, well, if we assume that this holds for all values less than n, then therefore it has to hold for n as well. And so what that is saying is if all of the dominoes before the nth domino fall over, they're going to knock the nth domino over. And then that's enough to prove it for all such integers n. So it sets off a chain of events. So what I want to practice today is taking a look at some statements and setting up and proving the base case and thinking about the induction step. And then we can fill in the details of the proof together. But I'd like you to do some work with these with some classmates first. So with induction, it's really like a two-step process. Handle the base case, then deal with the induction step. And so here was, so any questions about that, first of all? Okay, so then in the video, we considered the following example. So let's say we want to show that for all non-negative integers n, the nth derivative of e to the 2x is equal to 2n e to the 2x. Then just to kind of illustrate what these parts of the proof would be in this case, the base case here would be the smallest value for n. And so here we could think about the 0th derivative, which would just be the function itself. And then in the video, we talked about how this holds for the 0th case. When you take no derivatives, you get e to the 2x back, which is 2 to the 0th power times e to the 2x. Okay, and then next up is what's called this induction step. So now we're going to consider, we've already handled the case, the smallest value for n. Now we consider all other values of n, bigger than 0. And the induction hypothesis is we're going to assume that this statement holds for all values of k less than n, n bigger than or equal to our smallest value. So we're going to assume that when I take the kth derivative of e to the 2x, I get 2 to the k times e to the 2x for any integer k which is less than n. And we want to show that this is going to therefore hold for the case when we take the nth derivative. And so in this process, what we could do is we could recognize that the nth derivative of this expression is equal to taking the first derivative of the nth minus 1 derivative, right? And so from the inductive hypothesis, we've assumed that that for any value less than n, which would include n minus 1, this property holds. So for n minus 1, we can assume by the induction hypothesis that that does equal to n times e to the 2x. And then we now, after using this induction hypothesis, now we apply the nth derivative, one more derivative. And with that comes down this extra power of 2 And then we see that, yes, if it holds for smaller values of this integer, then it's going to follow for larger values of this integer. Thus, it's going to hold for all values of n. So any questions about this? This was in the video, but you didn't have a chance to ask a static video. Okay, and if you've been reading the book, you might notice that in the video, I did it a little bit differently than how the book outlines it. So in the textbook, they talk about mathematical induction. In the first section, they talk about strong mathematical induction in the second section, and other types of induction. So we're just going to consider one type of induction. I think it gets more confusing when we start to think about 10 different cases of induction, but we'll just think of like the most general case of induction, and we'll be able to apply this technique to any problems that would require some induction. But I do want to just kind of connect this to what you might be reading in the book. So in this case, the statement that we're trying to prove, P sub n, is this statement right here. And so here's our proof that we just walked through. And I'll just say the textbook doesn't do anything different in the base case. They do the induction step slightly differently in the sense that they don't assume all of the dominoes less than n fall over. They want to show that if the domino right before, if the n-1 domino falls over, then it's going to knock over n. And so let me just compare kind of their process to this. So if I were to redo the induction step according to the textbook, what they say is this, when they use this notation over here, this is exactly trying to say that we are going to assume the statement P is true for the kth case, and then we're going to try and show that it follows for the next case. So rather than, really the only difference is rather than assuming this holds for all values of k less than n, they just assume that it holds for the value k, and then they're going to try and show that it also has to hold for the next integer, which is k plus 1. And if you kind of look through this proof, it's essentially identical to the one that we have above. The only difference here is, again, they are, in the textbook, they just assume that this holds for one specific value of k, and then they try and show that it's going to hold for the next one. And the proof would follow exactly the same way. We would do the same technique. So I'll just say that the way that we did it above is the same as the way it's done down here. And we don't need to worry about redefining induction in other cases. The way that we're doing it is going to be able to apply to all of these cases. So I just want to explain that that's my motivation behind doing it, is to just talk about doing one mathematical induction that's going to work for all of the problems, as opposed to 10 different cases of doing virtually the same thing. Okay, are there any questions? So the plan for today is, here are, there's about 5 or 6 statements over on this sheet of things that we can prove, among other ways, by induction. So the first thing that I'd like us to focus on, and I can go through one example together just to let you know the exercise that I'd like you to do with the other problems, is just prove the base case, write out what the induction hypothesis is, and then write out what you would actually want to show to finish up that proof. And then we can talk about how we can show that together, since that might be the tricky part. And so I'll just say that this one over here, that's a homework problem. That's a tricky homework problem. That's your last homework problem. So we can at least get you started on that today a little bit. So let's say I'm going to do this exercise for question 2. And this is kind of another little game. And so the idea here is we're stacking all of these disks on top of each other. And what we'd like to do is be able to move all of these disks over here so that we have the same looking pyramid on the rightmost rod. And the way that I'm allowed to move these is I can't put any disk on top of a disk which is smaller than it. And the claim here is that we can do this no matter how many tiles we have. And moreover, we can actually show how many moves it will require to do that. And so this is pretty tricky process if you just try to do this. Think about doing this directly or contrapositive or something like that. So if you're kind of thinking about when does induction seem to make sense, it's when we're trying to prove statements that depend on some integer n. And we're going to try and prove this for all such values of n. So what I'd like you guys to do in your groups would be to set up like, okay, let's consider the base case and prove that at least the base case is going to work. So in this case, our base case would be the smallest value for n, right? Which in this case would be 1 disk. Okay, and so so now we're only really thinking about one disk over here. And again, the goal is to move all of these disks, in this case, one of them, over to the rightmost rod. So how could we do that in the base case when we just have one disk?
We pick it up and move it over to the rightmost rod.
That's right. So this is what's really nice about this process is that usually knocking the first domino over is pretty quick. And so there you go, right? Now we're done. That completes the puzzle. And how many moves did it take us to do it?
2n minus 1.
In one move, yeah. Okay, and so notice this checks out that 1 actually equals 2 to the first power minus 1. So the base case checks out. We can win, and we can show that it's only going to require 2 to the n minus 1 moves, in this case, 1 move. Okay, any questions about that? And what you'll see is that there's definitely a pattern and some common things that we're going to do in all of these cases with induction. So now we're going to consider values of the integer that are bigger than our base case, which was 1, and less than n. And the induction step, the induction hypothesis is going to be that we can solve this game if we have k disks from the start. And then we want to show that this is therefore going to show that we can solve this game if we have more than k pieces. So this is like assume statement P of k is true, but we just take it one step further in the sense that we assume this is true for all values of k less than 1, not just the immediate value right before it. And the thing that we would want to show that we can solve the puzzle in 2 to the n minus 1 moves. So it's like this piece over here is assuming that P of k is true. And this is what's called the inductive hypothesis. And then all of this stuff over here is what we need to show. And if we can do that, then we're done, right? Essentially, that again is showing first one goes down. If previous dominoes fall down, they're going to knock over the ones that come after it. So it's not different than what the textbook is doing. Maybe just I'm using slightly different notation with k and n as opposed to k and k plus 1. Okay, any questions so far? I'll just say that you can develop your own style when you're doing induction. So you don't have to write out every single time, we want to show this. But I will say that it's helpful to have some structure to fall back on. So if you're stuck on these problems, you can always start by writing this out. And sometimes just writing the sentence out, expressing what it is that we're trying to show actually helps. Okay, so what I'd like you to do in your groups is do the same sort of thing. Don't go through the whole proof, prove the base case, set up the induction hypothesis, and be sure it's clear what you would want to show with that induction hypothesis. And you might want to just leave some space when you do this, and we'll fill in the blanks as we fill in the details for some of these. So now you can see this, I hope. Yeah, so P of n, right, is just this entire statement up top. And so the base case we're going to consider here is, let's consider n is equal to 0. Then P of 0 is, sorry, not 0. Our first base case here is 1, right? So the first positive integer, the smallest positive integer is 1.
Is 0 considered a positive integer?
0 is not a positive number.
Oh, okay.
It would be considered a non-negative number, so that's why we considered it in the one that, yeah, for the derivative one, we had non-negative ones. But here, we're going to start with a positive integer, so that would be, that's like natural numbers, another way of saying the natural numbers, so that would be 1. So then P of 1 is just the statement. On the left side, I would have 1, and on the right side, I should have 1 plus times 1 plus 1 over 2. That does equal 1. So that takes care of the base case. And I'll just say, that's usually what's really nice about induction. If you're finding it really difficult to prove the base case, induction might not be the best method. But what happens is if the base case is easy to go, and then we see that there's some iterative process, then that sets us up really nicely for induction. And when you're writing these proofs on homework, I do want to see things written out like this way. It should be labeled what is the base case. It should be labeled what's going on in the induction step. And so for the induction step, it's always going to be the same thing. I'll just say the hypothesis So this inductive hypothesis is always going to be for all values of k bigger than or equal to our base case less than some integer n, we're going to assume that p of k is true. And that's the induction hypothesis always in induction, and we just need to replace in what is p of k. That's really the only thing we need to identify is what's the base value, and what is statement p of k. And we've already identified both of those things when we did the base case. So here we're going to say, let's let k if you want to get descriptive, it should be an integer. Okay, and what's significant about the 1 there, remember that was our base case. And that's what statement P is when I plug k into it. Okay, and we want to prove the same exact thing is true for values bigger than k. So as far as what I was asking you to do in your groups, this was the task here. Any questions about that? Okay, then let me do the same thing for one more problem, and then I do think it's good for us to finish a couple of these up so we have a complete proof. So please just let me know if you have any questions. Okay, so let's kind of think about question number 4. I don't know if you've had time to get this far, but this is what's called like an extension of De Morgan's law. And if you don't recall, De Morgan's law says that when we take the complement of the union of two sets, it's equal to the intersection of their complements. And this we proved on worksheet 6, I'll just say. So as we've been saying, you're allowed to use results that we've proven on the worksheets in class or on homework. So if you're kind of looking at this and you're like, I think I remember seeing something like this, you look through your old notes, you find that you've done it or we've done it together, then you don't have to reprove things. Okay, so here, what would the base case be?
N equals 2.
Yeah, so we're going to say, okay, if n equals 2, then we've got A1, the complement of A1 union A2 is equal to the intersection of their complements. Okay, done that, been there, don't need to relitigate that. But if you don't recall doing that, you certainly could prove this. So we call this the inductive or induction step. We use these interchangeably. Yeah, let me keep my coloring. So in this case, now we're going to say, let's let k be an integer. So that it's bigger than our base case, less than some integer n. And now we're going to assume that this statement is true, right? Our statement P of k, right? This is exactly statement Pn. So I'm going to assume this is true when we plug in k. Let me come to a new line. So that would be our assumption. And what we want to show is that for dominoes further on down the line from k, this also holds. And again, you do need to start this inductive step by stating the inductive hypothesis. You don't need to step, you don't need to state this is what I'm going to prove, but I do think it's helpful if you do that to keep you on track. All right, any questions? And yeah, I mean, I think the reason why I wanted you guys to just kind of set up this outline is that I do think it's useful to kind of do this one after the other before getting lost into the weeds, just so that you can focus on what's similar about all of these processes rather than focus on what's different about all of them. How we fill in the details is going to be different, but how we set all of these up is going to be the same in all of them. Any questions? Okay, so let's go back and take a look at this first one that we set up. And so so we've done one. We've set up the base case induction step for one. We did two together. We did four. So I might ask you to do this on the reading quiz for questions 3 and 5 and 6, the ones we didn't talk about today. I'm not going to ask you to prove them, just say what is the base case, for example. But let's do complete proofs for these two examples. Okay, so we'll come back to question number 1, which is asking us to verify this formula for the sum of the first n integers. Did anybody start to think about how we might be able to show this?
Do we substitute, what, k plus 1 in for k?
So I want to prove this. So we want to show this over here. So usually what's a good place to start is start with the left side of that equation and then show that we can get the right side of that equation. So I'm just going to write it out like this, right? If I sum up the first n integers, I would take 1 plus 2 plus 3 all the way up to n minus 1 plus n. And does anybody see how we can use the induction hypothesis at this point?
Well, the n minus 1 will cancel out the 1, giving us just 2 n's.
Sorry, this is, we could cancel out the ones, but that's actually getting us away from the induction hypothesis, right? So the induction hypothesis is this over here. And we've assumed this is true for all values of k less than n. Is n minus 1 less than n? It is, right? So that means all of this stuff right here, we can use the induction hypothesis on that. And that's what these induction problems typically look like, is let me write out the thing that I'm trying to prove. Look, embedded in that is a same property for a value, for a smaller value of n, and my induction hypothesis allows me to assume that property holds for values smaller than n. And so by the induction hypothesis, I can take all this stuff over here and all of this can get replaced with the assumption that we have over here, right? That I know for values of that are smaller than n, this holds. So if I add up the first n minus 1 integers, my value for k is n minus 1, right? And that, again, is less than n. So I can use this property by plugging in n minus 1 in for k back up here in our inductive hypothesis. So we would take n minus 1 times n minus 1 plus 1 all over 2. And what I'm plugging in is I'm replacing the k's that we had over here with the fact that k is the first n minus 1 terms. And so this actually gives me n minus 1 and then we still have a plus n. Okay, and so that part comes from the induction hypothesis, again, where we've just substituted k with n minus 1. Any questions? Okay, and then now we want to simplify this. So I can add this by putting them over a common denominator. So I've got n minus 1 And then when I take the n minus 1 plus 1, that just gives me n. And so if I want to put them over a common denominator, I'm going to multiply that n by 2 over 2. And then this gives us n squared minus n plus 2n over 2 which can be simplified to n times n plus 1 over 2. And that would be it. We've just now proven that if it holds for values less than n, it's going to hold for n. Okay, any questions? Okay, so let's think about the more extended De Morgan's law, question 4, where we have the base case. We're now doing the inductive step. And here's our assumption in green. And so again, when we're trying to prove the conclusion here, which is in blue, how it usually goes is you kind of start on this side and then you want to show this. You shouldn't assume the thing that you're trying to prove. So that's always a big caution there. So we're going to say, let's consider what we get when we do something like this. And seeing what happened in the previous one, sometimes it helps to just write out the term just before the nth term so that we can see where the induction might come in handy. And again, what we're hoping to show is that we can simplify that and get this out in the end, but we shouldn't assume that we can do this. Does anybody see how we might be able to use induction here?
You just do the same substituting, so everything up to a of n minus 1 is just a1 complement intersects a2 complement up to a k complement.
Careful, right? Because this is still trapped underneath this complement over here. But maybe let's think about it like this.
Just going to use De Morgan's law to rewrite it.
Basically, yeah, that's right. So let me just introduce some set x, which is equal to that. Okay, then what we can say is all of this stuff oops.
So this is reducing it down into the complement of the union of two sets, which is just De Morgan's law.
That's right.
Okay.
So we can write this as this set X union AN complement. Which we know from the base case from De Morgan's law oops. This is equal to this intersect that. we haven't quite gotten there yet, right? What we wanted to do was to prove this. And so far, we're here. And so what's missing?
Well, by the induction hypothesis, we know what X complement is.
That's right. So we haven't used the inductive hypothesis yet, but now we can. Since I know if this is X over here, then I know how to find the complement of this because we've assumed that it's true. Oh no, I can't scroll up. Here we go. Yeah, so we assumed it's true for values of k less than n. So n minus 1 is less than n. So we can say by the induction, we know that the complement of x is going to equal the intersection of all of these complements. And that basically crosses us over the finish line. Let's see. Okay, so this tells me that therefore x union an complement equals x complement intersect this. And then by the induction, we can now replace x complement with all of this stuff. And that was the goal, right? What we wanted to show. I left one of those off. Okay, so that's all the time we have. If you've got any questions, feel free to hang around. I just want to take a look at the homework that you guys have to work on for Monday. Let me share it with you. Yeah, so for the homework, I'll just say you should get going on a lot of these. I'll just say the last question, that's an optional problem, and I'll update in the homework assignment. So I'm not going to ask the grader to grade that one, but if you do it and you do it correctly, that's awesome. That's a tricky one. So we'll talk about that in class on Monday together as well. Okay, well, have a nice weekend, everyone. I have office hours tomorrow. I also have possibly jury duty tomorrow, so I'll find out as of 5 p.m. So if I do have jury duty tomorrow, I would rather be online helping you with math, but I can't do that. So I'll post an announcement later on tonight when I find out what my deal is for tomorrow. But if you do want to meet with me and I'm not available tomorrow, I'm happy to find the time on Friday.